Today, let's talk about vector control. Vector control, also known as field-oriented control, FOC. Its ultimate goal is to achieve independent and precise regulation of motor torque and speed. It works by aligning the coordinate system with the rotor flux direction. Using coordinate transformations, the stator current vector is decomposed into an excitation component and a torque component, enabling independent control of each. Step 1. Coordinate transformation. First, the AC currents in the motor's three-phase windings are sampled, yielding the three-phase AC signals, ABC. These ABC currents produce a rotating magnetic field with constant magnitude and angular velocity. These three AC signals, spaced 120 degrees apart, are decomposed and equivalently converted into two AC signals, I-alpha and I-beta, on a Cartesian coordinate system using complex number theory. Simply put, this transforms the three-phase stationary reference frame, ABC, into a two-phase stationary reference frame, alpha-beta. However, I-alpha and I-beta are still varying signals. If the stationary frame could be made to rotate at the same angular velocity as the rotating magnetic field, they would become relatively stationary. Therefore, by detecting the rotor's real-time position, a DQ reference frame rotating synchronously with the rotor flux is introduced. Here, the D-axis aligns with the rotor flux direction, and the Q-axis is perpendicular to it. The stationary alpha-beta frame is then transformed into this DQ rotating frame. This completes the transformation from the ABC three-phase stationary frame to the DQ two-phase rotating frame. Step 2. Decoupling control. After this transformation, the complex three-phase AC signals are represented as two stable DC quantities. The D-axis current component, ID, acts as the excitation current, controlling the magnetic field strength. The Q-axis current component, IQ, acts as the torque current, controlling the torque magnitude. By applying independent PI regulators to ID and IQ, dynamic decoupling and precise control of the magnetic field and torque are achieved. Step 3. Feedback and closed-loop control. The system continuously detects motor voltage and current. First, the difference between the target speed and the actual speed is fed into the speed regulator, which generates the Q-axis current reference, closing the speed control loop. Meanwhile, the D-axis current reference is typically set to 0 for maximum torque per ampere control. Subsequently, feedback values for ID and IQ are obtained via current sensors. These are compared to their respective reference values, and the errors are sent to their dedicated current regulators, closing the current control loops. Step 4. Inverse transformation and drive. The current regulators output the DQ-axis voltage references. These are then converted into alpha-beta axis voltage commands, V-alpha and V-beta, via the inverse Park transform. Finally, space vector pulse width modulation, SVPWM, uses V-alpha and V-beta to generate PWM signals. These control the VFD's power module to output the corresponding three-phase AC power, driving the motor. Vector control technology overcomes the nonlinear, multivariable coupled nature of AC motors. It enhances dynamic response and speed regulation accuracy, enables highly efficient energy conversion, and reduces torque ripple. It is particularly suited for applications demanding high starting torque, high speed accuracy, and high dynamic performance.